Okay, so now that we understand what a logarithm is, we're now going to look at some properties of logarithms. So I'd like you to find the following, okay, and then use your calculator to find these. These are the common logs, so that button's on your calculator, right? Log base 10. Okay, so let's look at this. Go ahead and do that. You can pause me and fill these in, okay? Okay, so this is asking 3 to what power equals 81? 3 to the fourth is 81. And on your calculator, if you take log, which remember that's log base 10, and that's on your calculator, log of 81 divided by log of 3, you get 4. And if you take natural log of 81 on your calculator, divided by natural log of 3, you get 4. Okay? We know that the log base 25 of 5 is a half because 25 to the 1/2 power equals 5. And interestingly enough, when I take the log of 5 divided by the log of 25, I get a half. And when I take natural log of 5 divided by natural log of 25, I get a half. 9 to what power equals 1? 9 to the 0 power equals 1. And when I take the log of 1 divided by the log of 9, I get 0. When I take the natural log of 1 divided by the natural log of 9, I get 0. Okay, so this is a property that always happens. It's called the change of base formula. If I have the log base A of m, if I want to find what that is, I can take the log some other base of m divided by the log that same base of a. Okay, so we choose to use log base 10 because that's on our calculator. And it's just log. It's the common log. We don't write the 10 because it's so common. Or we choose to use the log base e because that's on our calculator, written as ln, natural log. Okay, so that works out perfectly. So if I want to find an approximate rational solution to 1.03 to the x power equals 5, then I am going to rewrite this as a log. Okay, this is saying log base 1.03 of 5 equals x, right? 1.03 to the x power equals 5. Another way to write that in log form is log base 1.03 of 5 equals x. Well, let's use the change of base formula, which tells me if I have the log base something of m, I can take the log base something else of m divided by that same log base something else of this base. So I'm going to use my calculator. I'm going to use natural log. I'm going to take the natural log of 5 divided by the natural log of 1.03. And that will give me my approximate solution. Okay, so I'm on my calculator. I'm taking natural log of 5 and my parenthesis, because the calculator puts a parenthesis in there, divided by the natural log of 1.03 and my parenthesis. I end up getting 54.4486. 54, it says round to 4 decimal places, 0.44, it'll actually be 87 because it's 0.448685. So I'm going to say 0.4487. Okay, so if I would like to check that and kind of make sure it's close, what I'm saying is that if I have 1.03 and raise it to the 54.4487 power, I should get about 5. That's what I'm saying. You know, we can always substitute our answer in for x. So on my calculator, I'm taking 1.03 upper, that up caret thing, okay, to the 54.4487 power. And when I do that, I get 5.000002216. So it's pretty close to 5. You know, I have some round off error there, but I'm pretty convinced that that's correct. Okay, that's how you use that. If $2,500 is invested at 6% compounded daily, then how long to the nearest day would it take the investment to double? Okay, so we're going to have to use our formula here that we've been using. The amount equals principal times 1 plus the interest rate over the number of times per month that is compounded to the NT, where T is the number of years. So a $2,500 investment, it's invested at 6% compounded daily. That's 365 times a year. 365 times, how long will it take for the investment to double? Well, that's what how long? So I need the T. I don't know. That's my time. But it's going to double, so this is going to end up being 5,000 is what we're saying. We want to know, when's our 2,500 originally going to turn into 5,000? It was at 6% compounded daily. 1 plus R over N. R is 6%. N is the number of times per year it's compounded every day. And to the N times T power. Okay, so I'm going to divide by 2,500. I get 2 equals. I'm also going to take 1 plus 0.06. 1 plus 0.06 divided by 365 is 1.0. It's a long decimal here. And I'm going to keep it there. 1.30164384 to the 365 T power. Okay, our exponent has our variable in it. Whenever we have this, guys, we're going to need to solve this using logarithms. Okay, I'm going to rewrite this as log base 1.000164384. Okay, that's my log of 2 equals 365t, right? That's the same as saying this base to this exponent equals 2. Divide by 365, log base 1.000164385 all over 365. Well, to do this top part, I'll use my new formula, and I'll just take log of 2 divided by log of 1.000164385 and divide that whole thing by 365. So I get my handy dandy calculator out here. And I'll be careful. I take the log of 2 and my parenthesis divided by the log of 1.000164385 and my parenthesis. Okay, I see what that whole answer is. It's like 4,216.955. Whatever, I'm going to divide that by 365 now, and I get 11.55. So about 11.55 years. Okay, about 11 and a half years for that to double. Okay. All right, some other properties then are the exponent rule. Now, we know that when you multiply like bases, you add the exponents. The logarithmic rule is if you have the log of a product, okay, then you add the logs. I'm going to take log base A of X plus log base A of Y. Just like here, I would add, this would be A to the X plus Y power, right? When you multiply like bases, you add the exponents. Here, when I divide like bases, I subtract the exponents. So this is going to be log base A of X minus log base A of Y. Just like here, it's A to the X minus Y. And if you have a power to a power, you multiply the exponents. Well, same thing here. If I have a power, really the log is a power, I'm going to multiply the Y times whatever the log base A of X is. I'm going to end up multiplying them. Anything to the 0 power is 1. Well, the log base anything of 1 is 0. All right, so if you know your exponent rules, I just like to put them beside each other. The exponent rules we knew, the log rules are very similar because logs really are exponents. So if we're going to write this as a single logarithm, this is the natural log of 12, okay? This was the natural log of the product 6 times 2. This is the log base 2 of, since this is subtracting 2 logs, it must have come from division. So this is the log base 2 of 5 is the answer to that one. This is the log of x squared minus 4 over x minus 2, which is the log of x plus 2x minus 2 if I factor that, divided by x minus 2. So I end up getting the log of x plus 2. Okay, a much simpler logarithm than to deal with all this. Okay, the log, if I have 2 logs added together, that came from the log of their product. So natural log of 12. When it's subtraction, it came from the log of their quotient. 25 divided by 5. Quotient. X squared minus 4 divided by x minus 2. And then we simplified that with some algebra. Going in the other direction, I would write this as the log base 2 of x plus the log base 2 of y plus the log base 2 of z, if they asked me to write it as a sum or difference. This would be the natural log of 5 to the negative x minus the natural log of 2. Since it was the natural log of division, we separate it as the natural log of the numerator minus the natural log of the denominator. The other thing we do is take this exponent and move it and multiply it by the natural log of 5. That will be the final answer. Here I have the natural log of the square root of x over the square root of 4. Okay, it's the square root of x over 4, so I'm just writing it that way. So that's the natural log of the square root of x minus the natural log of the square root of 4. Well, the square root of 4 is 2. I'm just going to write it like that. Now, square root of x, guys, we have to write as x to the 1/2 so that I remember to bring that exponent in front. 1/2 natural log of x minus natural log of 2 will be the simplified way of writing this, or the way to write it as they ask, as the sum or difference of multiples of logarithms. Okay, rewrite this expression in terms of the log base a of 5. Well, 25 is 5 squared. So I can write this as 2 times the log base a of 5. I just rewrote this expression in terms of the log base a of 5. This is the log base a of 5 to the 1/3. So that's 1/3 log base a of 5. Okay, these are even questions out of the book. Writing this as 2 and 5, well, I know that 0.4 is 4/10 or 2/5. So this is a log base a of 2 minus the log base a of 5. That's how I would rewrite this in terms of the log base a of 2 and the log base a of 5. This is a log base a of, let's see, what's half of 250? 125. Okay, so that's log base a of 125 plus log base a of 2. All right, since I knew I was looking for 2's and 5's. And the log base a, I don't know if you realize this, but 125 is 5 cubed. So I bring the 3 in front, and I have 3 log base a of 5 plus log base a of 2. This is the log base a of 5 over 10,000, right? 1, 2, 3, yeah, 4 decimal places. So that's log base a of 5 minus log base a of 10,000. Okay, so there's lots of ways to think of how to write this. I already have log base a of 5, which is great. 10,000 is 100 squared. So that's log base a of 5 minus 2 log base a of 100. And of course, 100 is 10 squared, right?